Unit operation classroom. Today we are discussing estimation of adiabatic CSTR feed temperature. How to do that? My name is Shekhar Bhattacharya. What is the problem? A first order homogeneous liquid phase reaction A to B. This is first order. Occurs in an adiabatic. There is no heat loss. Ideal mixed flow reactor operating at steady state. The volumetric flow rate is given, the volume of the reactor is given. At the reactor temperature 500 K, the reaction rate constant is given and the heat of reaction is given. So basically, if you looked at schematically, so let's say this is my mixed flow reactor here. This volumetric flow rate is given. We do not know what is the inlet temperature of the feed. There's an insulation around it, so there is no heat loss from this reactor. This is a liquid phase reactor. A equal to 0. Then called the expansion factor. This is reaction. So basically the value of A is given, heat of reaction is given. Okay? And the CP average, that means the C has to be the CP of the inlet coming feed and the mixed reactor here and the product which are going out. The CP average value is already given. So this is an exothermic reaction. So as you can see, there is a negative sign. So this is an exothermic reaction. So what it does basically, the heat is generated during the reaction, and of course that if this temperature must be lower than this temperature, so what happens? This feed as it comes in gets heated up. So this just balances that amount of heat needed to raise the sensible heat of the feed that's coming in is just balanced by the amount of heat generated inside the reactor. So that it really keeps on operating at steady state. And since this is a mixed flow reactor, this is operating at 500 K, we can assume that this is also coming out at 500 K. All right. So we have to find out what at the inlet, the feed temperature, we have to find out. This is a very standard problem. We calculate the residence time, volume of the reactor divided by the volumetric flow, that's 5 minutes. Okay. And so this is a liquid phase reaction. So this epsilon is bigger. So this is from Levensville. And this for a first order reaction, this K tau is equal to this one. So we have taken this one. We know the value of K, we know the value of tau, so we can calculate the value of XA, which is 5.6. This all the details are given in the website. Now, also, this is also for an adiabatic reactor. If we do the material and energy balance, you'll find that this is the equation. So I have just written it down. And we know the value of XA calculator. We know the CP average. We know this value. So we can immediately calculate the value of TE, which becomes at 444.44 Kelvin. So basically what happens if this temperature is maintained at 444.44 Kelvin, so let's say the cold feed comes in, there should be some kind of heat exchanger. From the heat exchanger, it should come out and it should be heated up to this particular temperature. If this value is correct, then of course this will automatically sustain the reaction continuously. Then this temperature will be maintained continuously at 500 K, and this will coming out at 500 K. So that's the importance of making a material and energy balance together. Is there a chemical process industry relevance of this problem? Yes, there's a solution polymerization of ethylene to produce polyethylene. This basically right here. This is also an exothermic reaction. They add a comonomer like 1-hexene or 1-octane, and there's some kind of a proprietary catalyst is used, and ethylene is dissolved in a hydrocarbon solvent, C5 to C12 or isoparaffin. So as it comes in, of course, the temperature is almost the same as in the problem. In this particular 500 range here. This is a liquid phase adiabatic CSTR, same as this one. A homogeneous solution of polyethylene dissolved in hydrocarbon daily comes out from here. So this is of course an industry relevance of this problem. So the final answer to this problem is 444.42 Kelvin.